Hi, I'm Rob and welcome to this, our 7th lesson in trigonometry. And in this lesson and the next lesson, we're going to start looking at a couple of practical applications of the techniques we covered in the first 6 lessons. So the first 6 lessons, we kind of have a look at how we solve triangles. So here we're going to look at how we can create diagrams like the ones we learned to solve in the first 6 lessons from a real world situation. So the first application we're going to look at is dealt with on page 89 of your notes, and that's working with angles of elevation and angles of depression. Right? So if you're looking straight ahead of you, so if that's a horizontal line, you're looking straight ahead of you, you're not going to be able to see something that's above you or below you. So if you want to see something that's above you, you're going to have to angle your line of sight upwards. You're going to look upwards at that. So take my horizontal line of sight and angle it upwards to see an object above me. So I'll angle line of sight upwards like that. That angle there is an angle of elevation. Okay, so it's a horizontal line of sight angled upwards to see something above you. All right. If you want to see something below, you're going to have to angle your line of sight downwards. So if I take my horizontal line of sight and angle it downwards to see something below me like that, that's an angle of depression. The most important thing is that angles of elevation and depression are formed from a horizontal line. It's always a horizontal line angled upwards or downwards will give you an angle of elevation or depression. So it's a horizontal line, horizontal to ground, or a horizontal line of sight angled upwards to point at something above, or angled downwards to point at something below. It's always from a horizontal line. All right? And angles of elevation are measured, as you can see on page 90, using a clinometer. So make sure you just have the name of that piece of equipment, that you know how to measure an angle of elevation. That if you can see that if I look through here, if I'm holding the clinometer horizontally, I get a reading of 0 degrees on this side. All right. If I angle it upwards to see something above me like that, I get a reading here and through the view screen here telling me how far above horizontal the clinometer is pointing now. So I've got my angle of elevation. Or if I angle it downwards like that to see something below, I get a reading both here and in the view screen telling me how many degrees below horizontal I am now to see an angle of depression. So angles of elevation and depression are measured using a clinometer, just by looking through here to see you can see the top or bottom, or the object above or object below. And this instrument will tell you how many degrees above or below horizontal you're looking. So it'll give you your angles of elevation and depression. If I'm holding this clinometer horizontally, perfectly horizontally, it gives me a reading of 0. Okay, indicating that the line of sight is horizontal. Now, one thing that's worth pointing out, and we'll look at a question or two on this shortly, and it's pointed out on page 90 of your notes, that remember, if you're standing on a hill, your clinometer doesn't know that. So your clinometer will always give you a reading from horizontal. So if, for example, if I was standing on a hill like this, right, and I was trying to find the angle of elevation to maybe the top of a tree or something, right? So if I'm standing here, and I use my clinometer to look upwards, I'm seeing that I can see the top of the tree through the clinometer, right? So I'm looking up like that so I can see the top of the tree. If the clinometer gives me a reading of 40 degrees, that angle there is not 40 degrees. Because the ground is not level, so this is not a horizontal line. Your clinometer will assume that the ground is level. So it'll say, right, if the ground was level at this point here, we'd have to angle that horizontal line upwards by 40 degrees. That's my 40 degree angle. That's my angle of elevation, right? So you can see that if I wanted to find the angle in here, in the triangle that I'm then going to solve, I would have to take my angle of elevation and subtract this angle here, the slope of the ground. So when you're dealing with problems where the ground is not level, when you're measuring angles of elevation or depression using a clinometer, the clinometer doesn't know that. So you would have to adjust the angles you get from your clinometer to give you the angles with the ground. So the angle with the ground and the angle of elevation are only the same thing if the ground is level, if the ground is horizontal. If the ground is not flat, you have to adjust the angles of elevation you get from your clinometer for the slope of the ground. By, in this case, subtract the slope of the ground, or you'd be adding it if you're looking downhill. And we'll have a look at a couple of examples of that now. So the key thing here to remember is that you always form angles of elevation or depression from horizontal lines. Okay, so if it's not a horizontal line, it's not an angle of elevation, it's not an angle of depression. So if you look at the question on page 91, question 7.1, which looks like this, again, just make sure you read the text carefully. So it does say in the question that a rocket is launched from level ground. Okay, so that means, remember, then the diagram here, that this here is a horizontal line. The line across the bottom there, level, is horizontal. Okay, from a point P on the ground at 2.1 kilometers, from the point of launch. So we've got the line down here at the bottom. This line here is 2.1 kilometers. That's filled in the diagram anyway. It says the angle of elevation at the bottom of the rocket is measured 10 seconds after the rocket takes off as 14.6 degrees. So you can see that because this bottom line here is horizontal, that's an angle of elevation there. So this here is an angle of elevation. It's a horizontal line angled upwards, so it's pointing in this case at the bottom of the rocket, right? So that's why the angle's marked in here is 14.6 degrees. That is an angle of elevation there. It's because it's a horizontal line angled upwards. It says find the height of the bottom of the rocket above the ground after 10 seconds. So it's this height we're looking for here, h. It's that distance we're looking for. Now notice he didn't mention the question that the rocket takes off vertically. He doesn't need to because he's told me in the diagram that's a right angle there. If that right angle wasn't there, he might have said, for example, that a rocket is launched from level ground and that the rocket takes off vertically. So those two words between them would mean that there is a right angle because vertical and level, or vertical and horizontal, form a right angle. So watch out for the language of the question there to make sure that all the information you need is provided. So once I realize that, you can see now the solving of this diagram is very straightforward. Okay, so to actually do the calculation now, we just have a triangle that looks like this. All right, and it's a very simple calculation. You can see we've got a triangle which we know is right angled. All right, we've got three pieces of information. We've got the right angle here, the 2.1 kilometers, the angle here, so the triangle can be solved. And you can see I can do this using the sine, cosine, or tan ratios because I do have a right angle in here. If I wanted to, if I subtract those two from 180, I could find this one up here and then use my sine rule. That's perfectly fine as well. Okay, remember the sine rule works whether the triangle is right angle or not, and you always have options, but I'm going to do it what I think is the quickest way by just using the trigonometric ratios. So if that's the right angle there, then that's the hypotenuse, that's the side that's not involved in this question. H here is opposite the angle we're dealing with, so that's the opposite there, and then 2.1, that's the adjacent. So the ratio that uses the opposite adjacent, remember, is the tan ratio. So the tan of 14.6 degrees is equal to opposite over adjacent. It's equal to h over 2.1. And then to get rid of the fraction on the right-hand side, we'll multiply both sides by 2.1, like that. So we're going to get 2.1 times tan 14.6 degrees is equal to h. And if I put that into my calculator, I get about 0.547. Now, just be careful. Practical question, watch the units. That we're told in the question that this distance here is in kilometers, which means so is the answer we get here. So that's 0.547 kilometers because it's 547,000. So it's almost exactly 547. It says in the question, give me answer to the nearest meter. So to convert from kilometers to meters, I want to multiply by 1,000. So I multiply that by 1,000, I get 547 meters. So to the nearest meter, that after 10 seconds, the rocket is 547 meters off the ground. So if we look at the next question, the question on page 92, question 7.2, it reads like this. It says, Christ the Redeemer is a statue located at the peak of the Corcovado mountain overlooking the city of Rio de Janeiro in Brazil. From a point A on level ground, so once again, we're told that the ground is level. Okay, so this line here is a horizontal line, the ground is level. The angle of elevation at the top of the statue is measured as 36.2. So you can see from the point A here, the angle of elevation is 36.2, and that is an angle of elevation because the ground is horizontal. So it's this horizontal line angled upwards, okay, to give us that angle there, 36.2 degrees. So that's the angle of elevation here, 36.2. All right, that one. So it says from a second point B, so from this point B here, okay, the second point over here, the angle of elevation at the top of the statue is 47.4. That makes sense. The closer to the statue you are, the more upwards you'll have to look to see the top of the statue. So the angle is greater there. But that's also an angle of elevation because, again, it's a horizontal line, okay, angled upwards to the point at the top of the statue. So it's 47.4 degrees. And it says B is 17 meters closer to the base of the statue than A. So the distance between A and B is this 17 meters over here, right? And we're asked to find the height of the statue. Now what I'm going to do is I'm going to get in here and fit in as much as I can. First of all, look at the word in the question, the height of the statue. So the word height means the vertical height, okay, from the top of the statue straight down. So if I go from the top of the statue straight down like that to here, that's the height, okay? And when it's the height of the word, that's a right angle there. So that height forms a right angle with the ground because the ground is horizontal. So I'm not trying to find the distance from here to the edge like that. I'm not trying to come out here, okay? It's the right angle I'm trying to form there. So I've got a right angle triangle here. If I go from the top of the statue straight down, that's the height of the statue. Now I can actually fill in a lot of angles here, can't I? Because if I've got a right angle triangle here, this angle at the top here, this one, you can see that's 90, that's 180. Take away this 90-degree angle here, and then take away the 47.4. So that angle up there is 42.6 degrees. So I'll fill that in. Right, that angle there is 42.6 degrees. And again, because the ground is level, it's a straight line, it means that this angle here and the 47.4 make up a straight line. So subtract 47.4 from 180, we get that angle there is 132.6 degrees. And then if I subtract these two angles here from 180, I can get the last remaining angle in that triangle there, which ends up being 11.2 degrees. Right? And I'm asked to find the height statue, which is this height here. Okay, so I'm just going to fill that information in the diagram like that, so I've got an idea of what I'm looking for here and what I know. So before I'm doing a real world problem like this, I tend to stop and do that first. Fill all the information I can in the diagram so I can get a better look at what it is I'm trying to solve, right? So if I've got this diagram here, there's a right angle there. We've got that H there. This angle up here is 42.6 degrees. Okay, this angle over here is 11.2 degrees. And this angle out here, that big one there, is 132.6 degrees. And that's the triangle I'm trying to solve. And now we're back to what we did in the previous lesson. We're just solving a compound shape here to see if I can find it. So again, the problem with finding H is I don't have any sides in this triangle here. This triangle can't be solved yet. Okay? But again, like we met in the previous lesson, this triangle can be, because I know this side here is 17 and I know all three angles. So I'm going to use the triangle on the left-hand side to find this side here, right? Let's call that X. And then once I've got X, the triangle on the right-hand side is then open for business, okay? So to solve this triangle here, you can see on the left-hand side, I can use my sine rule because there's my pairing there. And I've got this pairing here. So we've dealt with the sine rule a couple of times now. The key thing here is once I get here, I should now be an autopilot. Okay, it's not hard to do the calculation now. So we'll get 17 over sine over sine 11.2 degrees. Okay, that's that pair, the pair I know written as a fraction, and we've got x over sine 36.2 degrees, and those two fractions are equal. So I'll multiply both sides by the denominator on the right hand side, true of the fraction, like that, and they'll cancel. And I get 17 times sine 36.2 degrees over sine 11.2 degrees is equal to x. And that comes out at round about 51.7 meters. Roundabout. I'm just rounding that off. So the red line there is 51.7 meters. So you can see I now know that this is 51.7. And then like our previous question, the triangle on the left-hand side can now be solved. Okay, and you notice because this triangle is right angled, I've got lots of options here. I can, of course, use my sine rule if I want to, because I've got a pairing here. Because the triangle is right angled, I can use the sine, cosine, or tan ratios if I prefer. So I'm going to use the sine ratio here, I think, because if I use this angle here, if I work with that angle there, you can see that opposite right angle, the 51.7, that's the hypotenuse. Okay, and if I'm using this angle here, H is the opposite. And opposite hypotenuse, remember, means the sine ratio. The adjacent down here is the one I don't need. I don't know what that is, nor am I asked to find it at this stage. So I'll use the sine ratio. So sine of 47.4 degrees is equal to opposite over hypotenuse, which is h over 51.7. So if you multiply both sides by 51.7 there to remove the fractions, the fraction on the right-hand side, you get 51.7 times sine 47.4 degrees is equal to h. And the question says to find the height of the statue, that it comes out at round about 38, and my answer is in meters. So it's about 38 meters there is the height of the statue. Okay, so two very simple sine rule calculations once I spot what the triangle I'm trying to solve looks like. All right, and then part 2 says, the base of the pedestal of the statue is 7.6 meters wide. How far is A from the base of the pedestal? So how far is this point here, A, away from the base of the pedestal? Now, let me worry about the base of the pedestal in a moment. Okay, what I want to find, first of all, I think, is I want to try and find that full distance there. Okay, So let me get that if nothing else. Even I'm not sure what to do with the base of the pedestal's width. Okay, let me just find that and that blue distance there. How far is A from this point here? Because again, you can see now, if I ignore the red line in here altogether, if I ignore that altogether for a second, okay, so look, if you look at kind of the bigger triangle here just for a moment, right? So you can see in the case of that big triangle, it's right angled. We've got a 36.2 degree angle over here, and we now know what H is. So we now know that this side over here is 38. So I think now I can use right angle trigonometry to find that blue line there, to find how far A is away from this point here, okay, which we look at now in a second. So if I want to name the sides here, this is the opposite, okay? It's opposite 36.2 degree angle. That's the hypotenuse there. That's the one we're not concerned with. And this one here, we just call this blue side here X, and that's the adjacent. So opposite adjacent means tan. So the tan of 36.2 degrees is equal to opposite over adjacent, 38 over X. Okay? So to remove the X, then to remove the fractions, we'll multiply both sides by the denominator X, because again, they'll cancel on the right-hand side. So I'll just get X times tan 36.2 degrees is equal to 38. And then divide by this guy here to leave the X by itself on the left-hand side. So X then is 38 over tan 36.2. And if I put that into my calculator, X over tan, 38 over tan 36.2, it's about 51.9 meters. Okay? So 51.9 meters then is that full distance there, the blue line, right? Now, why did you tell me the width of the pedestal? It said the base of the pedestal of the statue is 7.6 meters wide. How far is A from the base of the pedestal? So if you look at the diagram in the question again, this diagram here, okay? That, remember what we've got at this stage here, we have just found this distance from here, sorry, that full distance there. Okay, so the distance from here right across to there. Okay, so with the vertical line coming down that way. So that distance there is 51.9 meters, right? Now we're told in the question that the information you gave me is that the width of the base of the pedestal here is 7.6 meters. So the base of the pedestal is 7.6 meters wide. So there's a slight judgment call I'm going to make here that distance there, because remember the distance we're trying to find is from here, from that point there to A. Because the question says how far is A from the edge of the pedestal, which is this point here. So I got to subtract this little bit here from the 51.9 I just found. And I'm going to make a judgment call here that that's half the 7.6 meters. Because you can see here that the pose of the statue is symmetrical. So I'm assuming that if I go from the very top point here, I hit the very center of the base below it here. So that distance there, and the two distances there are the same. All right? So, okay, so those two distances are the same here. So this distance here and this distance here are both half of 7.6. That's 3.8. So I think if I take my 51.9 that I just found, subtract that 3.8 there, half the width of the base, I think I've got the answer I'm looking for. So what I'm thinking there is that the distance I'm looking for, it's 51.9 meters. Take away 3.8 meters, and that comes out about 48.1 meters. And once down to the nearest meter, so that's about 48 meters between A and the edge of the pedestal. So if we look at the next question on page 94, it looks like this. So it says, a tree stands on ground which is inclined at 7 degrees to the horizontal. So remember, inclined means slope. So this time the ground is not level. Okay, so we're dealing with ground which is not level, that it's inclined at 7 degrees to the horizontal, all right? The angle of elevation at the top of the tree from the point P is 34 degrees. And the point P is 22 meters from the base of the tree. We're asked a couple of questions from there. So notice in this case here that first of all, this angle here is not an angle of elevation because it's not formed from a horizontal line. This line here is not horizontal. So because that's not a horizontal line angled upwards, that's not an angle of elevation, right? So the way to think about that is if you can imagine that's the point P there, all right? Now remember, when you get a reading from your clinometer assumes that it's horizontal. So if the ground was horizontal at the point B, like P like that, that would be an angle of elevation there. So that angle there is 34 degrees. It's a horizontal line at P, angled upwards to point to the top of the tree, right? So if I want to find this angle in here, the angle in it with the ground, that's in the triangle I'm trying to solve, remember you can see what I need to do is subtract that 7 degrees there, that's the slope of the ground, because these two lines here are parallel. Okay, so those two angles there are corresponding. So that's a 7-degree angle there, that's the slope of the ground. So if I take the angle of elevation, 34 degrees, and subtract the slope of the ground, I get 27 degrees now. That's why that's a 27-degree angle. So you can see the question part 1 says, explain why the angle with the ground is at P is 27 degrees. So explain why that's 27 degrees. All you're going to be mentioning there is the fact that the ground is not level. So the angle of elevation has to be adjusted for the slope of the ground. Now, anything that gets across the idea that that's not an angle of elevation because the ground isn't level is what you're trying to talk about there. All right, so that's the reason why that's a 27-degree angle. It's because the ground is not level, so we have to adjust the angle of elevation for the slope of the ground. And you'll notice as well then on the diagram that when we're trying, you know, so once I know that's 27 degrees there, I can actually fill in all the other angles here because this line here is horizontal, right? Because we're told in the question that it's inclined at 7 degrees horizontal, and we're asked to find the height of the tree, which will be in a second. Remember, the height of the tree is a vertical line coming down to the top of the tree like that. So there's a vertical line representing the height of the tree and a horizontal line here. So there's the right angle in this diagram. There's a right angle here. That's the big thing in a question of this type. So find the right angle. So because we're told that the ground is sloped at 7 degrees to the horizontal, it means that dotted line at the bottom there is a horizontal line. The height of the tree will be a vertical one. So there's your right angle. So you can see now I can fill in all the remaining angles because to find this angle here, that one, I'll just subtract the 90-degree angle and the 7 degrees from 180 because the three angles of the triangle add up to 180. So this angle out here is going to end up being 83 degrees, that angle. And then this one here, because this line here is a straight line coming down here, subtract 83 from 180, you get that this angle out here is 97 degrees. And then finally, in this triangle here, you can see I've got 97 and 27. If I subtract both of those from 180, I get that angle up there is 56 degrees. So as usual, I'm reading the text very carefully, and I'm filling in all of the measurements like that. So I actually know all of the angles in this triangle here. I know one of the sides, and now the triangle can be solved. Okay? So if you look at the kind of the diagram here, as it appears, we kind of filled in those, the 83, the 97, the 56. And this side here is 22. That's the measurement that was given. Part 2 says, how would the angle of elevation be measured? All you're going to mention there is the piece of equipment used, which remember is a clinometer. Okay, so we just mentioned the word clinometer there. You don't have to describe how to use one. Just be aware that there's a piece of equipment we use there, the clinometer, to do that. And then part 3 says, find the height of the tree. So we're asked to find the height of the tree, which is this thing here, this bit here. That's the height of the tree, h. Okay, so you can see now, if we look at the triangle now, all the practical bells and whistles are gone now. Now we can just focus on the triangle that we're trying to solve. Is it right angled? No. Okay, because we've got a 97-degree angle in there. So can I use my sine rule? Yes, I can. There's a pairing. See it, 56 and 22. There's another pairing there. So now finding h is just a very straightforward sine rule calculation. So once we get as far as the calculation should be quite quick. So I'm not going to spend much time on the calculation. So it's going to be 22 over sine 56 degrees. There's the pair we know there's a fraction. It's going to be h over sine 27 degrees. And those two fractions are equal. So we multiply both sides by this guy here. I'll get 22 times sine 27 degrees over sine 56 degrees is equal to h. And if I put that into my calculator and push a couple of buttons, it comes out at about 12.047. It says to give me the nearest meter, so it's about 12 meters. So the height of the tree is 12 meters. This height here is 12 meters, right? And then in part 4, it says from a different point Q, which is only 14 meters from the base of the tree, what would the angle of elevation at the top of the tree be, correct to the nearest degree? Okay, so there's a point down here somewhere, which is only 14 meters from the base of the tree. We're asked to find what the angle of elevation would be there. So just notice if I was trying to re-sketch that diagram just to see what it is I'm looking at, all right? So there's the slope of the ground again, and there's the tree there. So obviously this angle here is not going to change. That's still a 97-degree angle there. Okay, we've got a 97-degree angle here. We've got the point Q here, which we now know is only 14 meters from the base of the tree, right? We know the height of the tree is the 12 meters we had a moment ago. So I think that's the triangle I'm going to be trying to solve. So I'll just fit in the measurement of what I know. Obviously, the angle between the tree and the ground won't change. All right, this measurement is now 14. The height of the tree is 12 from our previous calculation. And I think I'm going to try and find this angle here. Okay, try and find theta. That's the angle that we form with the ground at the point Q. Okay, so to solve the triangle, can I use my sine rule? No, not yet, because I don't have a pairing. I know this side but not the angle. I know this side but not the angle. I know the angle but not the side. So I can't use my sine rule. I'd have to use my cosine rule. And the only thing I can use the cosine rule to find is this side x over here. So I'll have to do that. It's not what I want, but again, this is just another one of those two-step calculations. Okay? So if I use my cosine rule, remember that the cosine rule, a squared equals b squared plus c squared minus 2bc cosine a. The one thing I've got to be careful of is the side that goes by itself on the left-hand side is the one that's opposite the angle. And because that's the angle we're working with here, the side opposite that is the x. So the x goes on the left, and the other two numbers, 12 and 14, go on the right. So it's x squared equals 12 squared plus 14 squared minus 2 times 12 times 14 times cosine 97 degrees. And I'll just put that entire right-hand side into my calculator now. So I get x squared is equal to, it's about 380.95. Again, remember, it doesn't matter how many decimal places you write down there. Just keep the whole number on your calculator display screen so you can use the answer function in a second. And then that means x is going to be the square root of that, 380.95, square root of your answer. And that comes out at about 19.5 meters. So this side here now is about 19.5 meters, that side. And you can see now that I've got that, now I can use my sine rule. Because now I've got a pairing here, I can now use my sine rule to find the angle I'm looking for. So it's not uncommon for solving a real world problem to require a two-step solution. There's no guarantee it'll be a single calculation. So if I use my sine rule now, again, it's an angle I'm looking for, the angle's on top. So sine 97 degrees over 19.5 will be equal to sine theta over 12. Okay, so we multiply both sides by the 12 there to remove the fraction on the right-hand side. They'll cancel. And I get sine theta on the right is equal to 12 times sine 97 degrees over 19.5. And that number comes out, it's round about 0.6108. Okay, as I said, it doesn't matter how many decimal places you write down there. Just keep the whole number on your calculator display screen. So you can use the answer function next, because theta is the inverse sine of that number, which comes out at around about 37.6 degrees. Okay, which is 38 degrees, because that's the nearest degree. So 38 degrees. Now, again, be careful. That's not your answer. 38 degrees, remember, is this angle in here. So that angle there is 38 degrees. If we were asked for the angle of elevation at the point Q, remember the angle of elevation would be from a horizontal line. So if the ground was level at the point Q here, the ground was horizontal, that's an angle of elevation. That horizontal line angle, that's your angle of elevation there, not just the 38. So you can see I've got to take the 38 here and add the slope of the ground to tell me what the angle of elevation would be at that point. Okay, so again, just visualizing the diagram there, that the angle of elevation is going to be the angle with the ground plus the slope of the ground. So the angle of elevation is going to be 38 degrees plus 7 degrees, which is 45 degrees. That's the angle of elevation with at the point Q. So if we look at the last angle of elevation question, then this one on page 96, it says a wooden tower stands at the very top of a hill. The hill is inclined at an angle of 8 degrees to the horizontal. So again, the ground is not level. It's inclined at 8 degrees to the horizontal. So this dotted line down here, that's a horizontal line. Okay, so that's a horizontal. It's the one that's inclined at 8 degrees from. It says from a point P on the slope, the angle of elevation at the top of the tower is 52 degrees. And from a point Q on the slope, the angle of elevation at the top of the tower is 31 degrees. And we're told the distance between P and Q is 25.4 meters. That's on the diagram. So you'll notice that again, that these two angles here have already been adjusted for the slope of the ground. So that angle there with the ground at the point P, 44 degrees, is the angle of elevation 52. Take away the slope of the ground. Take away the 8-degree slope of the ground at the bottom. All right. So it's take away this angle down here. And the same with the angle the angle with the ground at the point Q. It's the angle of elevation 31, subtract the slope of the ground. So when we're dealing with ground that's not level, we have to adjust angles of elevation for the slope of the ground to find what the slope with the ground itself is. All right? And then remember to fill in the remaining measurements, because in part 1 we're asked to find the height of the tower. So again, if I drop a vertical line coming down here, the vertical line, because height implies the vertical height, okay, straight down like that. Bring this horizontal line across here, like that. There's the right angle. So once we locate a right angle, I can fill in all the remaining angles. So if I subtract the right angle and the 8 degrees from 180, we get this angle here is 82 degrees. And then there's a straight line there. So this angle here, subtract 82 from 180, you get 98 degrees, that angle there. And then if I subtract the 44 and the 98 from 180, I can get this angle up the top here. So that angle up there is 38 degrees. Again, because you've got a straight line here, that angle there is 180, take away 44, which is 136. Okay, so that angle there is 136 degrees. And then finally, this angle up here, if I subtract 23 and 136 from 180 for that triangle there, I get the one at the top there is 21 degrees. So when I'm doing a question this time, I want to get in there and fill in all the measurements I can. So it makes the triangles I'm trying to solve much easier. I can see at a glance what the best way to solve the triangle is. So there's the diagram there, and just kind of done out with all those measurements filled in. I'm asked to find h over here, and you can see now it's a question we've had a look at a couple of times, so I won't dwell on it now. I can't solve this triangle directly because I don't know any of its sides, but this one here I can because I know this side here, so I can use my sine rule. There's a pairing there, and there's a pairing. I'll use the sine rule to find this side here, x first. So what you get there is you'll get that 25.4 over sine 21 degrees is equal to x over sine 23 degrees. Multiply both sides by this guy here, you'll get 25.4 times sine 23 degrees over sine 21 degrees is equal to x. And when you do that, x comes out at about 27.7 meters. So that's this line here, is 27.7. And once I know that that side there is 27.7, that gives me my pairing now, remember, to solve the triangle on the right-hand side. Okay, so we'll get the 27.7 over sine 98 degrees is equal to h over sine 44 degrees. Okay, and again, multiplying both sides by this guy here, you'll get 27.7 times sine 44 degrees over sine 98 degrees is equal to h, and that's about 19.4 meters. It says to one decimal place, so it's about 19.4 meters. All right, is the height of the tower. And then part 2 on the next page, the last part, it says a zip line is run from the top of the tower to a point on the slope exactly halfway between P and Q. So there's a point down here somewhere, exactly halfway between P and Q, and we're running a zip line from the top of the tower down to that point there. We're asked to find the length of that zip line correct to one decimal place. So if I just kind of resketch the triangle as I'm going to use it here, because there's a lot of information, that diagram's getting quite busy. It's kind of hard to make out what I know and don't know. So if I just kind of resketch the diagram, just the triangle itself, so there's the ground there, and there's the tower. So obviously this angle here will remain the same. So that's still 98 degrees in there, all right? There's the point that we're dealing with here, a point that's halfway, that's the point that's halfway between P and Q. And that's the zip line going up to the top of the tower that way, right? We know the tower here, from the calculation we just did, the height of the tower is 19.4 meters, all right? And we're trying to find this distance here. Now, at the moment, you can see that the problem is that I only know 2 things about the triangle. I don't have enough information yet to deal with this, right? So if I go back to my original diagram, I think here And this might require a bit of thought. So you might find yourself stopping and chewing your pencil for a couple of minutes here, trying to puzzle this out. Again, it's not a single step calculation, all right? I think from this diagram here, using the sine rule there, I can find that side, right? So I can find how far the point P, remember that's P there. So I can find how far P is in the base of the tower, right? And then if the point where the zip line ends on the ground is halfway between P and Q, then this distance here from P to the point where the zip line hits is half 25.4. So if I find that green line there from this triangle and then add half 25.4, I think that's this distance here, and now the triangle's solvable. So again, it's not simple, it's not straightforward, it requires a bit of thought, but that's my plan here. Okay, so I'm going to try and find that green line there first. I'll just call that y for a second, and I'll just use my sine rule on that triangle there to find y. So obviously we've got this pairing here. So 27.7 over sine 98 degrees is equal to y over sine 38 degrees. That's the pairing there. So again, if I multiply both sides by this guy, I get 27.7 times sine 38 degrees over sine 98 is equal to y. And that comes out at about 17.2. So that means this bit here, the green line there, that's 17.2. That's how far P is away from the base of the tower. And then because the point where the zip line ends is halfway between P and Q, from P to that point there is half of 25.4, which is 12.7. So if I have 25.4, I get 12.7. So if I get that distance, 17.2 plus 12.7, that's 29.9. That's how far the point I'm looking for, where the zip line ends, is away from the base of the tower. In other words, that's this side here. And now our triangle is solvable to find the value for x. So a bit of thought required there, which is not uncommon. But now I've got down to a triangle I can solve, so now there's no problem from here. So to solve that triangle there, you can see I can't use my sine rule because I don't have a pairing. I know this side but not the angle. I know this side but not the angle. I know this angle but not the side. So that's a job for the cosine rule. Okay, and remember the side that goes by itself on the left-hand side is the one that's opposite the angle, which is going to be the x. So I get x squared is equal to 29.9 squared plus 19.4 squared minus 2 times 29.9 times 19.4 times cosine 98 degrees. And if I put that entire right-hand side straight into my calculator, I get it's around about 1431.83. I'll keep that whole decimal number on my calculator display screen and then get the square root of that answer. Right, like that. And if I do that, it comes out at about 30, it says to one decimal place, that's about 37.8 meters. That's the length of my zip line. That's a really nice little question. So that's kind of the different variations of working with angles of elevation, particularly paying attention to what happens when the ground isn't level. So in the next lesson, we'll have a look at one other application of working with triangles of this type, and that's dealing with three-dimensional problems. That'll be our next lesson.